So, hi everyone, welcome to this NPTEL course on combinatorics. So, this is week 10 problem solving session for this NPTEL course combinatorics. So, let's start. So, let me share my screen and uh, send some notes. Okay. Mm, mm, what happened? 10, 14, 14, 15. So, let's start. Okay, let's just quickly recall the theory what we have done in this week. So help me in recalling the things. So wait a second. Okay, so let's start. So recall. So what we have done in this week. So help me in recalling. So we started with discharging methods and its applications. So what is discharging method? Uh, So basically, we give charge to each vertex and faces, and then do discharging by like distributing the charge to corners of vertices and faces, and then see what conclusion we can draw from there. We done several examples in the classes as well, and we will do some here as well. So then what we see something like conditions like reducibility of some configurations and reducibility of configurations. Then we see in the path of this application of this discharging method, we see all these things, and then unavoidability of an reducible configuration, something like that. Unavoidability. What else? After this, we have seen we have proved this theorem, but we know a stronger version than this. We have proved this that any planar graph with no 4, 5 up to 11 cycles has 3 coloring. Like in last lecture, we have seen that any planar graph has a 5 coloring, but we already know from class lectures that we haven't did this proof, but this is a very advanced proof, and we have the instructor stated this theorem that any plane graph can be colored by 4 colors, but this result is saying something more. Any planar graph with no 4, 5 up to 11 cycle has 3 coloring. In fact, more is known. Basically, some conjectures in this direction, which has been disproved recently, as instructor mentioned that if there is the conjecture says that if there is no 4-5 cycle, then this is a 3 coloring, but which has been disproved. So after this, we will do some problems in this direction as well, and then we see the Polya theories related problems, like which says that you have given n squares and suppose m squares and n colors, how many way you can color it, and then you restrict some condition, give like when you restricted to some rotation, when you restricted to some rotation or some like two if like 180-degree rotation, 270-degree rotation, or some reflection are allowed, then how many different colorings are there, all these things are the in Polya theories. And then what else? Then we have seen group actions. So have you covered this week lectures, or I need to recall these things in detail?
I have not covered all of it, and I have particular doubt. I actually don't know. I was having some confusions in symmetric groups and group actions
Okay, I will recall.
classes.
Okay,
Yeah.
I will do all these. Okay, fine. So tell me what is your doubt, be precise. So I can, okay, let me start giving you definition of group action, then you tell me your doubt, I will try to solve that. Okay.
Okay.
So suppose G is a group and X is a set. You are familiar with the definition of a group, or I need to give?
Yes, I know the definition of the.
Okay. So G is a group, X is a set. We say G X on set X uh, if we have a map phi mapping G cross X to X such that we satisfy the following condition, I should write. Uh, which satisfies the following condition. Okay. First condition is what? Phi of G comma X. What is that condition? Phi of E comma X is should be E comma X should be phi of X comma E, and the second condition is phi of uh, G comma HX. uh, Phi of G comma phi of H comma X is what? Phi of GH comma X. These two are conditions, and is there anything else? These two are only things,
Identity.
right? What identity?
So the E EX is should be X, or there was something.
E
If
phi
E is
E,
the identity of G,
yes, phi E comma X is phi X comma E. That's what I write now.
that's
He doesn't
so
write this function phi. He just write E X is X is, right? You want to me write this, right?
yeah.
Okay. Anything else? This is the definition, I guess. Yeah, this should be correct. This is the
So
definition.
X phi takes the tuple E comma X, that's fine, but X is
Huh?
not in G na. So can we
Huh.
actually write it like that? Phi X.
We shouldn't write in that way. Okay, so I am writing this way. So we should write only phi comma X is X.
Yeah.
Yeah, that's correct. Good. So this is the definition. So, but let's see some example. Then the things will become clear, because like just by seeing abstract theory, things not become clear. So suppose I takes with simple example. Suppose we have a group G. Let's say start with random group G, and G act on itself by how you are defining action by G cross G to G. We have natural group operation for any element G comma H. It goes to their multiplication GH. Like G comma dot is a group, and this is acting on itself basically. G is acting on itself by this action. So what is the orbit of this action? How many orbit this action has? Like start with basic question. You know definition of orbit, or I need to give? Hmm?
I can't recall the definition.
Definition is this thing: uh, G dot X such that G belongs to G. Like collection of all multiples, G multiples of X. Orbit of X is basically all G multiples of X. So how many orbits in this action have? Can you see?
Here's something. So orbit of X is G of X, or it's G.
G of X, G dot X, all G multiples of X. Like basically of this form, G dot X, orbit of an element X belongs to X.
Okay, so okay. Oh,
हाँ हाँ.
uh, so it is
So
the set with all GHs, all for different values of G.
so what is this orbit of any element? Suppose orbit of any element. What is the orbit of any element? Like pick any element of G. What is the orbit of that element?
That is that times uh, I mean that then uh,
Suppose orbit
squares.
of an
So here we have G cross G, then that goes to the square.
suppose orbit of an identity. What is the orbit of identity?
That should be identity itself, no?
Why? Orbit of identity, not stabilizer of identity. I'm asking orbit of identity or G multiples of identity. What are they?
Then G itself.
Yes. G dot E such that G belongs to G. So this is what? Full G. So now
Okay.
I guess he done this in class. This forms an equivalence relation. So partitions the set. So you know from basic set theory that like equivalence class partitions the set into disjoint unions. Basically, either two equivalence classes are identical or they are disjoint. So basically,
Yes.
so all equivalence classes are going to same. So basically, all the elements orbits are going to be same. Orbit of E is equals to orbit of G for all G belongs to G. Since what the argument? Equivalence classes are either identical or disjoint. So there is nothing to for disjoint, so they should be identical. So, but this you can, yeah, this is the basic argument. But you can also see this is a basic example of your this burnside lemma he mentioned in last class, right? Have you covered that, or should I need to write this statement?
No, I have not covered that yet.
Oh, okay, so let me write the statement and tell me the terms if you could understood some terms. So this is your burnside lemma, right? Uh, Burnside lemma. So this says that X be a finite set. Let X be a finite set and G be a subgroup of of Sn. Why he says G is a subgroup of, okay, and G is a subgroup of Sn. Any group is a subgroup of Sn basically. That you have. Are you able to prove this theorem? Any group is a subgroup of Sn, isomorphic to subgroup of Sn. Have you done this proof or not?
No, I have not done group theory.
Okay, so I will do this proof. This is easy. Maybe you can see this is obviously right. If you have some simple or like, okay, I will tell you the proof. G be a subgroup of Sn. In fact, G is any arbitrary group acting on X. You can assume that. For a finite permutation phi belongs to G. What is the fixed subgroup corresponding to this element? Pi is defined as set of all X belongs to X such that pi acting on this element X is basically X itself. So So, okay. So, what is this means? So, under any permutation, this element is fixed. But what is the permutation? So, permutation, what is permutations? You know, na? This symmetric group Sn. You know this symmetric group Sn?
No, I have about tossed to the for the
Okay.
what the operator in the symmetric group.
Okay. Let me tell you. Symmetric group Sn. Sn. Okay. So, what is elements here basically? Elements are functions. Elements of Sn are functions bijective functions. Bijective means one on two functions. Bijective functions from 1 2 up to n to 1 2 up to n. Basically n cardinality set to n cardinality set. This is my n set. This is also my n set. So now if you have any function, let's say f, so f will take some value at 1, some value at 2, any bijective function, some value at f2, something f2, f1, f2, so on, so on, so on, some value at fn, right? Now this is bijective, injective, so it takes all value of codomain, and injective, so it takes for different value, different value. Suppose at 1 it takes some value k, at 1 it takes k, so you can write in a cycle form. So basically 1 takes the value k takes some value, like then you can see what is the value of fk. So fk takes, let's say, some value j, then you can similarly continue j takes some value. Once the value 1 is repeated, continue, close this bracket. This is the close form of writing this permutation. So if fj equals to 1, close this bracket, then continue with other terms basically.
Oh,
Are you getting? Are
yes,
you
yes.
getting me on? So let me give you for three cardinality set. So suppose you have this three cardinality set.
So
One,
here we care about the orders, right?
we care about orders. In this permutation close form, we care about orders. Yes.
Yes.
So these are basically functions. So suppose how many function from three cardinality set to three cardinality, bijective function from three cardinality set to three cardinality set. That you should know.
Yes, that's 3 to the power 3.
Bijective function I am asking, not all function.
Oh,
That you should tell me. Okay. Can you give me argument, or I should tell you? From n cardinality set to n cardinality set, how many bijective functions? This is precisely n factorial, and this is obvious to see, right? First element has n choices. Once one choice is fixed there, then second element has n minus one choices. So on, so on. At last, you have only one choice, right? Am I audible? Hello. Hello.
hello. Yeah.
Am I
Uh,
audible?
yeah. My internet had some
Okay.
issues.
So I am saying this is precisely n factorial now. You can't
Yes,
see it
yes. Yeah.
because this is first one has n choices, second one has n minus, last one has n one choice basically,
Yeah.
right? So this is from this n set to n set basically n factorial. So the here are how many number of bijective function is n factorial. So now let's write these functions, all these functions precisely basically f1, f2, f2, n factorial, which is equals to 3 factorial is equals to 6. So let's write these all 6 functions and then their closed form, so then things will be clear to you, right? So what is f1? F1 is identity function, taking the value 1 to 1, 2 to 2, 3 to 3. Then what is f2? F2 takes 1 to 2, 2 to 1, 3 to 3. What is f3? F3, let's say, take 1 to 3, 2 to 2, 3 to f1, f2, f3, f4. F4 takes, let's say, 1 to 1, 2 to 3, 3 to 1. But then F5 takes 1 to 2, 2 to 3, 3 to 1. And then F6 takes 1 to uh, 1 to 1 to 3, 2 to uh, let's say 3 to 2, 2 to 1. Yes. So these are all functions, 6 function, right?
Yes.
So can you write now their closed form? How you write first one?
So we'll start with 1.
Then there
Then
is nothing. 1 goes to 1 only.
yeah.
So this bracket will be closed. Then 2 goes to 2. This bracket will be closed. Then 3 goes to 3. This bracket will be closed. Right?
So the closed form has each element in their brackets if all elements are not covered, or
What you
do
mean?
we need to? So
What do you
if
mean?
I want to give a closed form of say this function, then in the case where suppose each element led to the next element,
Hmm?
we write them without the brackets in a single bracket, 1 comma 2 comma 3 or something like that.
Like you want to write this, let's say write this. You want to
Yeah,
say
this
this?
I'm asking. This is different than the
Yes,
each
yes, this is
element, right?
completely different. If you are writing 1, 2, 3 in a single bracket, that means image of 1 is 2, to image of 2 is 3, to image of 3 is 1. This means
Yes,
this.
yes,
And this means image of 1 is 1, image of 2 is 2, image of 3 is 3.
yes,
Are you getting or not?
yes. Yeah, I got.
And now can you write close form of second one?
So this starts with 1 comma 2, uh, 1 comma 2 in
1,
a single bracket. Yeah.
1, 2. We
Uh,
didn't write comma here, huh?
okay.
This
Oh,
is
okay.
just a convention. We directly write numbers. And then
And
3
then 3.
single.
Yes.
Huh. And then F3,
So this is 1 3
1, 3,
and then just 2.
then just 2. Right. What is F4?
F4 should have the third function 3 to 2. No. Yeah.
Huh. Huh.
So this is just 1
Huh?
and then 2 3.
2, 3. What
No,
is F5?
no. Oh,
Sorry, 2, 3 in
less
a single
than, yeah.
bracket. Yeah. Yes.
So
Now
this
what is
is
F5?
1 2 3 in a single.
And this is?
This is 1 3 2.
Now you can see both these are different thing, huh?
Yeah.
So that's why order. So now comes up, this is the elements. What is the operation basically? Operation is function. What is the group operation? If you have elements, functions, so what is the natural choice for group operation? Their composition, function composition, right?
Yes.
So you have one function from n cardinality set to n cardinal set, another function from n cardinality, both are bijective, so composition is going to be bijective. So so yeah, so this is function composition. So f1 dot f2 is basically f1 o f2. So can you see composition now? Let me write example from there only. 1 2 3 and 1 3 2. What is their composition? What is their composition? Can you write it?
So okay. So we take 1 to 2 and then 2 to
This is your f1, this is your f2, and you want to write f1 o f2, composition f2. So first you will see along f2. So that means image of 1 is in f2 is 3, then in f1 image of 3 is 1.
1.
So that means 1 is, you are starting with 1 and is it closes on 1 only, right? So this bracket is
Yes.
closed. Then you start with 2, image of 2 is 1, image of 1 is 2. So 2 is again closed. And image of 3,
Is 2
image of
and
3
2
is
is
2,
3.
and so 3 is again closed, right?
Yes.
So that means this is identity. So f1 is the inverse of f2, right?
Yes. Yes. Yeah.
F1 or f2 is identity. That means f1 is the inverse of f2.
Okay.
Now you can see similarly, now you got how to do compose basically, right?
Yeah.
Without writing functions and all that, just by seeing cycles closed form. So let's write these two, 1 3 and 1 2. Let's, you have these two permutation. How you compose them?
So one goes to 2, but here should I?
So this is a convention basically. I should write here or like write full permutation. But if you see some standard text like dummy put or something, they avoid writing this identity permutation. This is by naturally. This is obvious that if you are working like on three set on S3, so if you have single bracket, they avoid it writing. Assume that if anything is not written, that means this comes in a single bracket. Its image is identity itself basically. 3 goes to
Okay.
3, so he is avoiding writing that. So all these standard texts assume this basically. So 1 2 3. So for you I can write, but this is standard convention. So 1 3 and 2. So this is your first permutation, and this is your sigma 1, and 1 2 and 3, this is your second permutation. So if anything is not written in permutation, and like let's say permutation is on 5 symbols 1 to 5, and there is a one cycle 1 to 4 and 5 is missing, so this is natural to assume that 5 is a singleton image, basically
Okay.
itself image. So how you compose them? Can you compose?
So one goes to two, and then two goes to itself. So it's
Huh?
the first
1
element
goes to
is
2. Huh. Now 2 goes to,
two goes to itself in sigma one.
no, you are not composing correctly. 1 goes to 2 and
Yeah.
then 2 goes to itself, right? So image
Yeah.
of 1 is 2. Now 2 goes to uh, 2 goes to 1 and 1 goes to 3. So so 2 goes to 3. Now 3 goes to itself and 3 goes to 1, so bracket is closed, right? Have you got
So
all?
how did you go from two to so in the sigma two you I understand that one and two are in a single bracket. So one has its image two, right? Then
Yes,
two
let me
goes
write the
to
function for you. 1, 2, 3. So in sigma 2, what is happening in sigma 2? So sigma 2 image of 1 is 2. So
yeah.
this function 1 is 2, then image of 2 is 1, image of 2 is 1, and 3 is here. This is your sigma 2. And then you are going along sigma 1. Sigma 1 image of 1 is 3, and image of 3 is 1, and image of 2 is 2, right? So now if you take image of 1, 1 goes to under composition, sigma 2 or sigma 1, 1 goes to 2 and 2 goes to 2. So image in composition, 1 is image of 1 is 2. Then use image of 2, 2 goes to 1, 1 goes to 3. Image of 2 is 3. Then 3 goes to 3, 3 goes to 1. So the image of 3 is 1, right?
Yes.
Is this clear?
Yeah. Uh,
Okay. You are saying something?
when we write on the right hand side,
Huh?
if I start with one, so
Huh?
I
Then okay, 1 goes to 2,
yeah,
then 2 goes to itself, right? This is
yeah,
singleton bracket.
yeah,
So that means 1 goes to 2.
yes.
Then you start with 2, 2 goes to 1, and 1 goes to 3. So that means 2 goes to 3. Now start with 3, 3 goes to itself, and 3 goes to 1. So that means 3 goes to 1. So bracket close.
Oh, okay. Okay, I understand.
Okay. So I hope things are now clear. What is this group and what is the operations there? So what you want to ask in permutation group, now you can ask.
Oh, I suppose the yeah, understanding the operation was main problem. I'm sorry.
Okay.
Okay.
Now it is clear now.
Yeah, yeah.
Huh. So here I am writing burnside lemma. I should write it completely. So I should write full statement. So
So yes, here you said G is a subgroup of Sn.
huh.
So Sn was defined to be finite on the n set, right?
Permutation on n set, on
Yeah.
bijective function on n set. Huh.
So what if G is not finite? Then you can
But G is finite group, I am assuming.
okay. So you assume
Yes.
okay.
So any finite group is a subgroup of Sn. I will prove this theorem for you. Any
Yes.
finite group is a isomorphic to subgroup of Sn. In fact, you can see this proof now. Maybe you can see this clearly. I can give you a hint. Let's say until then you can think about this. Suppose you have any group G. Now you have here the set of, suppose cardinal G is a finite group. Cardinality of G is n. Let's say. So suppose cardinality of G is n, and this is a set of, on right hand side, take this thing, set of all bijective functions on this n symbols on let's say on G, basically on G. So this is same as taking set of all bijective function on n symbols. Then you can see, send any element G to here phi G. What is phi G means? Phi G is a mapping from G to G. How? For any element I send it to GH, multiplication by left from G. So this is a bijective function you can see, because for any element G you have inverse G inverse, so that will corresponding give you phi G inverse, that you have to argue. I will argue, basically I will give you a proof. Okay, so now you can see its image is a subgroup of this right hand side, and this right hand side is nothing but Sn. So its image, and up now you need to claim that this map is injective, so you are done. So G is isomorphic to a subgroup of Sn. So this is the basic idea.
Uh, Excuse me if I am asking a bit of stupid question, but uh, uh, I'm thinking about the definition of the subgroup. It was that whatever set was used in suppose S,
Hmm?
you have a subset of that, and you take the operation and apply it
Ah,
there. So if it's
yes,
closed, then
yes,
it's a
that's
subgroup,
correct.
right?
That's
So
correct.
I'm
That's
trying to
correct.
relate it to this. I mean,
Yeah, that's correct. This is same here. I am saying that this map. So okay, I will prove this rigorously, but I am just giving you hint. So
okay.
suppose you have, I am giving you this morphism phi, which is basically sending G to phi G. So now this phi G is a subgroup here. I am claiming. I will claim that this subgroup is a phi G image, image, image of phi, image of phi. This morphism phi is subgroup of G. This is symbol for subgroup of G, and no, sorry, subgroup of Sn. I will claim one thing. Second thing, first claim is this thing, and second claim is phi is injective. I will claim these two things. That will prove that, this will prove that image of phi, basically image of phi, phi G, मतलब image of phi कहने का मतलब phi G ही है, phi of capital G, image of full G. Phi G is isomorphic to G, because this is injective on phi G, it is surjective as well, and phi G is subgroup of Sn. So G is isomorphic to a subgroup of Sn. So that's what I want to prove. This is Kelly's theorem. So have you got it, something intuition or somewhat? Maybe you have easily proved this. Yeah, this is now obvious more or less, because injectivity is more or less obvious just by group operations, nothing more than that. And image phi is subgroup of Sn. This is more or less clear, because this is a group homomorphism. Under group homomorphism, uh, uh, image of a subgroup is a subgroup. Image of a group is a group, basically. Yeah. But all this I will prove. If you are not getting, since you have said
I
that.
will try to prove this. I'd like to try this later at home instead of
Okay,
doing it.
fine. So
Yeah.
good. If you want to try at home, that's good. Huh. If you didn't get, you can refer any book, a standard book. If you want to this abstract algebra course, you can follow Damit Foot, anything else. But I
Can you
prefer Damit
recommend a book for abstract algebra?
Damit Foot. This is a standard text. You can read ring theory, group theory, basic commutative algebra, field theory, all things from this book. This is a standard text. Like, yeah,
Dumit and food.
yeah,
Okay.
Damit and Foote,
Okay.
abstract algebra.
Yeah.
Yeah. So, yeah, I'm mentioning this burnside lemma. I should write full statement. Let me write burnside lemma. Burnside lemma. So this says that X be a finite set and G be a subgroup of Sn for a permutation phi belongs to G. This statement will be used in a problem. That's why I'm writing this again. So fixed subgroup of pi is X belongs to X, such that pi X is X. And so now from definition, you can see what is this fixed pi, basically. Pi X is equals to X. That means what? Pi is a one cycle. So that means fixed pi, fixed pi is number of one length cycles in pi, right? Because only one length cycle are going to be fixed. Otherwise, if cycle has length 2, then image 1, image 2, 2 image 1, so on, so on. right?
Yes. Yes.
So if you want to see some topological example of this group action and this quotient, you can visualize something like, suppose you have a circle, you can give it Z2 action, right? These are all things like if you do some higher math course like group geometry group theory or something, these are basic examples in that course. Like in even in algebraic topology, all these will come. Suppose you have circle, so you can take in Z2 action on it basically. And how you will take Z2 action? So Z2 have only two elements, right? 0, 1. So treat 0 as an identity element is any how this element act, element maps any element to itself, and 1 is basically inverting the elements. So inverting means taking antipodal image. So what is the quotient space under this? When you can think about this and can tell me later what is the quotient space. This is a geometric visualization picture, so that's why I gave you. So so if y mod g denotes the set of orbits in G, then cardinality of y mod G is 1 over order G times summation pi belongs to G fixed pi. So initially, like in one example where we have taken group action of G on itself, we have seen that this cardinality of y mod G is basically 1, right? We have seen only there is only one orbit, so we have seen this one, but we can verify from this theorem as well, because 1 upon number of G, cardinality of G basically, and pi belongs to G fixed pi, basically this is going to be what? So if you are running over an element phi G fixed pi, fixed of this pi is basically only itself
Each singleton element. So it will, yeah, basically uh, uh, cardinality of
identity
G.
element. Identity element fixes everything and nothing else than fix anything. So only identity fixes everything. So fix of identity and anything, nothing apart from identity, nothing fixes anything. So fix of identity, which is itself G only. So this is cardinality of G. So this is basically 1. So this is another example of burnside lemma for G mod H for previous action we have considered. Action we have seen. Yeah. Is this clear?
Yes.
Why this fixed identity, nothing else? Is it clear or not?
Yeah, if we have any other than identity, then it will end up its image will end up elsewhere and not in itself.
So but how you'll prove this rigorously? Is it clear to you or not?
So the if so, I suppose the fix itself requires it to be identity. Otherwise, it won't work.
Yeah, it's correct. In this case, at least. Yes. At least in this case, it is correct, but in general, it is not. Some example we will see. Yeah. I will give you some example. S5 case I will do. Yeah. Okay. We are continuing this group action. So let's do a problem in your assignment. I have seen this group action problem. So let's do that also. Then we'll do other problems. Uh, Assignment. Wait a second. I'm opening the assignment, but this internet is not working. Huh. So you are familiar with this group? Tell me. Group Z5. Are you familiar with this Z5 group or not? If not, I can tell you because the problem is asking about this.
Yeah, I'm not, but is my if I guess is it the first five elements of Z
Yes.
integers
Yes. 0, 1, 2 up to 5 elements are this. And what is the operation?
addition?
Addition. How addition? Like how you will add 5 and 4? What is 5? addition 4.
Oh yes, it will not.
This is called integer modulo 5 group. In general, Zn is integer modulo n group. Modulo 5. So how this group is defined, let me tell you. So as you correctly guess, uh, let me explain Zn. So this will be more general for you. Zn, integer modulo n. So what is I mean? Elements are 1, 2 up to 0, 1, 2 up to n, 1, 2 up to n. And what is group operation? Group operation is addition modulo n. Modulo n. What I mean by that? So basically, so so suppose you have let's say a comma v belongs to this set. Let's say this set S. A comma b belongs to S. So how you will define their sum as a plus b is equals to some element r. Then we define in integer. This sum is okay. Integer modulo n. So this sum I will write in this way, plus n. So whenever I will write this sum, and this is usual sum in integer, this plus. So a plus b equals to r in some integer. So now what I mean by this a direct sum b, define integer modulo sum a direct sum b n as remainder of uh, remainder when r is divided by n. Then we divide r by n. R by n. So basically, what is this mean? Uh, r by, I should write in this way. R by n. R by n. So what is this means? This means r is equals to n a plus b for a comma b belongs to z plus union 0. I should write union 0. So this is the thing. So is this definition clear to you?
Yes.
So can you now
So
define?
this
So
is just the usual definition for mod, right?
yes, this is
Right.
usual definition for mod. So I feel okay. Are you familiar with user definition? I don't know. Okay, so that's why I explained. So
Yeah.
0, 1, 2, 3, 4, 5. So sorry, 5 is 0 again. So I should write 0, 1, 2, 3, 4. So here I also write what 0, 1, 2 up to n minus 1 I should write because I write 0 already. So right. So can you define some now of each elements? So that will be good. So let's write some for you. So maybe you on this will clear for you. Things. Can you say now what is this? Is obvious. 0 sum 1 is 1. 0 sum 1, 2, 3, 4. Now what is 1 sum 0? This is 1. This is 1 sum 1, 2. 1 sum 2, 3. 3 sum 1, 4. What is 4 sum 1?
Uh, 1.
How? I mean Z5.
Oh, so in Jet5 we take mod 5, right? So
Yes.
4 plus 1 is 5. Yeah, so it's 0.
Yes. Now can you define this row for me? What is 2 sum 0? This is
2.
2. This is 3. This is 4. This is
This is again 0.
this is
This is 1.
now this is
This is again 0. 1, 2, 3, 1, 2, 3.
yeah. Okay. Good. So we have defined this group Z5. So now the problem is this question. Consider the set of 5 cross 5 map of 5 cross 5 matrices with entries in Z5, entries in Z5. Z5 I already explained you. Let S5 be symmetric group on n symbols. What I explained you. On n symbols. So now S5 be symmetric group on n symbols. So define the action of S5 on this, and let's say this is the notation for this set, all 5 cross 5 matrices with entries in Z5. The notation for this is M5 cross 5 in Z5. This is the notation. Let S5 act on this M5 cross 5 over Z5. So how this element will be look like? Elements here, A belongs to here. Let's say A be some matrices here. So how A will be look like? A will be something 5 cross 5 matrix. So here it will have some column, 1 column, 2 column, 3 column, 4 column. I should write 5 columns. So uh, so it will have 5 columns. So I am writing this just to explain you. So this is 1 column, this is 2 column, this is 3 column, this is 4 column, this is 5 column. So C1, C2, C3, C4, C5. So now how this S5 acting on this A, for any sigma belongs to S5 and A belongs to M5 cross 5 over Z5, how you are defining this action? Sigma dot A is basically you are making a new matrix, let's say B, where B is equals to sigma. I should write how I should write A of sigma. I should write in this way maybe. Uh, uh, B is equals to A of sigma 1, A of sigma 2, so on, A of sigma 5. So I should write. Let's write this as what is A1, A2, AN. Let's write this as A1. This is A1, this is A2, this is A3, this is A4, this is A5, this thing. So permutes row basically, right? S5 acts in this way on S5. So action is clear to you or not? So are
Oh,
you with me?
and
Yeah.
here for the first column,
Huh.
A1,
Huh.
A sigma 1 is corresponding to A1, right?
No, no. A sigma 1 is image of 1 under this permutation is on S5 means 5 symbols. So in sigma, basically 1 has some image. In this sigma permutation, 1 has some image, right? This is element of
Yes.
S5. So this sigma 1 denotes the image of 1 basically.
Okay. Okay. Okay.
Sigma 2 denotes image of 2. So now what is this doing basically? So image of 1 will be something from 1 to 5, between 1 to 5, 2, 3, 4, something like that. So suppose image of 1 is 3. Let's say this permutation. So that means first row A3 become first row in B. This is what it means basically, right? First column in B basically. I'm saying row, but first column, right?
Oh, oh, so uh, can you repeat again? I didn't
Huh.
catch.
So let me give you example. Suppose sigma is basically 1, 3, 2, 4, and 5 itself. These are identity permutation. Now A is your any arbitrary matrix. So what will this do? What will this sigma dot A? Sigma dot A will be A of sigma 1. Sigma 1 is 3. So A3, first column will be A3, second column will be uh,
Two
second column
itself.
will be
A2. A2.
sigma 2, so which is 2. Third column will be
Okay,
sigma 3,
yes.
sigma 3 is,
Yeah.
so basically columns will are getting permuted.
Okay.
Are you getting this or not?
Yes. Yeah. Yeah.
Yeah. So now let's do this problem. So this problem is saying compute the following. First one, find the smallest subgroup of the matrix. Sorry, smallest. Why I'm saying smallest. Let's write this stabilizer because you don't know this. Okay. Smallest and how to find stabilizer subgroup of the matrix A, which is 1, 2, 3, 4, 0, 0, 4, 2, 1, 3, 1, 2, 3, 4, 0, 4, 0, 0, 4, 2, 1, 3, 1, 2, 3, 4, 0.
What is the stabilizer? So stabilizer subgroup.
Okay, let me define. So stabilizer of an element x belongs to x. How it is defined? Suppose gx on x and x belongs to x. So stabilizer of x is basically uh, g belongs to g such that gx is equals to x. Set of all elements of g which fixes this element. These are the stabilizer of this element or fix the element fixing this element.
You are finding this with respect to the mapping, with respect to the uh, sigma we gave before.
Yes, the action I gave you before. Yeah,
Yes, yes.
action of Z5 on S5. I gave you the action with respect to that action. So can you compute it? What is the stabilizer subgroup of this?
That only had. Can you go to the action before
Yes.
upwards in the page? Yes. Yeah, yeah. So that was 1, 2, 3, and basically everything else remained the same.
What else? What you want to say? That I
Can
gave
you?
you for one permutation. How you are defining action that I gave you, na? Suppose sigma is this thing. I gave you this example. This is example. If sigma is this permutation, then how it will permute? But here sigma is any permutation because this is an element of S5. Sigma is an element of S5. So now sigma. So you have to find out this all possible over all possible
Oh, okay.
elements which are fixing this element A, right? So, so how you are thinking this? So you are doing first time, so this will be good for you because otherwise this is obvious. But you are doing first time, so this is good. You can think. So g dot x, you need sigma dot x is x basically. So now first row should be fixed. So first row elements of first column should be fixed. So first column is basically third column, first column and fifth column are same as you are observing from this matrix, right?
Yes.
So what you can conclude? Can you conclude something now? What are the possible choices of permutation? You should think now. Use the product rule and think. सॉरी प्रोडक्ट रूल इसमें यूज तो नहीं होता हाँ इसमें प्रोडक्ट रूल का क्या ही यूज होगा दैट्स करेक्ट मतलब बेसिकली यू हैव टू कंप्यूट व्हेन यू हैव टू फाइंड द साइज देन यू कैन यूज द कंप्यूट मतलब हाँ आई विल टेल यू वन प्रॉब्लम रिलेटेड टू दैट ओके दिस इज जस्ट अबाउट स्टेबलाइजर सो यू कैन टेल मी सो व्हाट इज द पॉसिबल चॉइसेस फॉर परमुटेशन which fixing this element. What are the
I'm a bit
possible
confused
images of
in
one?
what is the
Suppose if sigma is a permutation in S5 which fixes this A, so what is the possible choices of image of one under this? What can be possible image of one under this permutation? One can go to one itself, one can go
yes,
to one, three, one can go to five, right? One can go only these three choices because these
yes,
three
yeah.
columns are same. Where two can go?
Uh, two can go. You are asking in terms of columns.
Yes, in columns only because the action is defined in terms of columns. Na?
So
So two
two
can
is
go.
alternates between the second and third place.
Second and fourth place. 04213 and 04213. These are second and fourth columns, right? Are you getting?
Yeah, yeah, yeah.
So now
Oh, okay. Yeah.
what are the possible permutation? One is the obviously identity. So can you write all possible permutation? One is identity under which image of one is one, image of two is two, image of three is three, image of four is four, image of five is five, right?
Yes.
That fixes everything. So one permutation is identity one. What else? Can you write all? Another one you can take image of one, one itself, image of two, two itself, image of three, five, and five, three, then four itself, right? This will work.
Yeah.
Then similarly, you can make all possible choices. How many possible choices are going to be there? Can you? I guess you should see it easily.
Six.
No, you are incorrect. So let me give you all choices. So now this happens. So you have permuted three and five. Now you can do one, three, and everything else fixes. So basically identity one, three. Then you can do three, five, which is already done. One, five. Apart from this, everything fixed. Then uh, two, four. Uh, then all possible products. So then uh, uh, so then 3 5 1 5 3 5 comma 3 5 2 4, then 3 5 sorry 3 5 1 3 1 5, then 1 3 2 4. Now three permutation 1 3 5 and then 1 3 5. हाँ सॉरी मैंने कुछ गलत तो नहीं लिख दिया ना? हाँ मैंने कुछ गलत लिख दिया लग रहा है. हाँ आई राइट सम मिस्टेक्स, यू शुड टेल मी. मैंने ये गड़बड़ कर दिया. क्या गड़बड़ कर दिया? ये गड़बड़ कर दिया. वन, दो को मिटाओ. सो 1 3 1 5 1 3 1 5 and 3 5, right? So these are three here and 2 4 1 is here, and then you have to take all possible products. So 1 3 and 2 4, there is going to be 1 1 3 2 4. So let me write 1 3 1 3 2 4. Then what? 1
One
3
five
5
two four.
1 5 2 4 3 5 2 4. Now then 1 3 5 and 1 3 5 2 4 are there. How much this? How many?
This is one, two.
I am missing one thing, right? I am missing something. 1 5 3 and 1 5 3 2 4. Now how many this? 1, 2, 3, 4, 5, 6, 7, 8, 9. Ah, I did some wrong again. I did some wrong. 1, 3, 1, 5, 2, 4.
So in each case, so
This is 4,
in each case, can we
5,
switch?
6,
So we have 3
7.
5, so we can have 5 3 2.
Hmm? 5,
As
3,
we
2
have
cannot have na. 5, 3 we
no
cannot have
no
na.
no no not 5 3 2, but if we have 3 5, then can we have 5 3 also?
5, 3 and 3, 5 both are same.
Acha, so the changes to asymmetric. Okay.
So what? What you want to say? Because 5, 3 is saying 3 image is 5, 5 image is 3. 1, 3, 1. Okay, 6 to 1, 2, 3, 4, 5, 6. 12. We have 12. We should have 12 elements. So how many? How much we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, we are correct. That's correct. Good. So are you able to follow how I did this?
Uh, I'll have to take a look at it again. I
Yes,
think.
you can. You can have a look and tell me. Yes, that's. So basically, what I observed where I can send first column, where I can send third column, where I can send fifth column. So I can exchange all these things. So I have take permutation accordingly. So they will fix and corresponding to second column also. And then I did all the permutation.
Okay. Okay. Yes. So
Have
how
you
did
got
you
it? Or
come up with the stabilizer in the first place?
okay. So let me tell you this way. You can think in this way basically. So first observe this thing that first, third, and fifth columns are equal, right? First,
Yes.
third,
First.
and fifth columns are equal.
Okay.
So then what?
Then second and fourth.
So this means first, this subgroup I am defining in this way, which consists of all these corresponding to these columns exchange basically. So basically one is identity, then 1 3, 1 5, 3 5, and 1 3 5, and 1 5 3. These all will lie in a stabilizer because when I am writing 1 3, that means 2 4 5 all are fixes. When I am writing 1 5, that means 3 4 all are fixes. Basically 3 goes to 3, 4 goes to 4, 5 goes to 5. So that is the convention I already mentioned you. So all
Okay.
these lies in their stabilizer. That is clear, na?
Yes.
This subgroup H lies in stabilizer. Is this clear or not?
Yes.
Because everything 1 3 3 1 are both are same. Both
Yeah.
columns are same. So this subgroup lies in a stabilizer. Now see, observe second and fourth columns are equal. So that means what? So you have this subgroup which consists of identity
2
and
4.
2 4.
Yeah.
Yeah. So this subgroup is in stabilize. This subgroup is also going to be in stabilizer, right?
Yes.
So now you take the product of both these two. Like,
Okay.
so you have required 12 elements, right?
Yeah.
So is this clear?
Yes.
If you have some doubt, ask because you are reading first time this group theory type of stuff. Is this clear or not?
Yeah. I
And
think I'm clear on it now.
okay. So if not, you can ask me again at later. Okay. So now this is a stabilizer we have computed for this matrix A. Now the second problem is asking find the matrix under the same action. Find the matrices find the matrices fixed by the permutation 1, 2, 3, 4, 5 under the group action. The group action. Further, compute the cardinality of the set. Of the set. Fixed point of this permutation. 1, 2, 3, 4, 5. You have to compute this set cardinality. Yeah. So find the matrices fixed by the permutation this thing. So can you see this? Entries are going to be over Z5 of matrices. So have you understood the problem or not? What you have to do? You have to find the matrices which are fixed by the permutation this thing. So what
Uh,
this means basically? Can you understand the problem or
so
not?
we treat 1, 2, 3 columns similarly and 4, 5 similarly.
Yes. So what?
So um,
Sorry. Uh, so this means this is your A1, this is your A2, this is your A3, this is your A4, this is your A5. So now he is saying that this matrix is fixed by the permutation. So अगर ये permutation, if this permutation fixing this A1, 2, 3, so if this matrix A is fixed by this permutation, that means what will happen? That means A1 should be same as A sigma 1, right?
yes,
So that means what is A sigma 1? A sigma 1
2,
is A2.
A2, yes.
So A1 is same as A2. So similarly, A2 is
2 is
should
same
be
as
same as A sigma
A3,
2. What is A sigma 2?
A3,
So A2 should be same as A3. Now, what A3 should be same as A sigma 3. What is A sigma
1
3?
again.
Yeah. So A3 should be same as A1. So A1, A2, A3 should be same, right?
Yes,
So these three columns should be same. But each column you have 5 entries, right? Because this matrix is a 5 cross 5 and entries over Z5. So each slot you have 5 choices and they are going to be same here and here as well, right?
yeah.
So how many choices for this column?
So, so we have 5 factorial choices.
5 factorial.
So
Entries
we
can be
are
repeated. Here we have 5 choices, here we have 5 choices, here we have 5 choices, here 5, here 5.
okay. So are we? What are we choosing from? Any numbers or only 5 numbers as Z5?
Only from Z5. Z5.
Okay, so the number. Okay, oh, I was assuming the numbers can't repeat. Uh,
So what?
So that's 5 to the power 5.
Yes. So A1 have 5 to the power 5 choices. And similarly, A4 and since this permutation, this matrix is fixed by 4, 5. So that means A4 should be same as A sigma 4, but sigma 4 is 5. So that means A4 should be same as A5, right?
Yes.
So A4 should be same as A5. So this is going to be same. Now, how many choices for A4?
So similarly, it has also 5 to the power 5 choices, and then I suppose
Yes,
the matrix altogether has 5 to the power 10 choices.
yes. So, so, so A have 5 to the power 10 choices. So what we need to compute? We need to compute the cardinality of the set 6 of 1, 2, 3, 4, 5. 6 of 1, 2, 3, 4, 5. This set cardinality is going to be 5 to the power 10, and we have computed precisely all the elements, how they will look like, right? Correct or
Yes.
not?
Yeah.
Okay. So you have got this or no? Or some doubt?
Uh,
You can ask.
in the can you go back to the question again?
Yes.
when they say find the matrices, this is sufficient to give that these
Yeah,
columns will
I
be the
gave you
same.
all the
Yeah.
you cannot write 5 to the power 10 matrices, na?
No, I was thinking maybe more some yeah.
You can give, basically you can write how many, what I precisely give you how the matrices will look like. Basically at first
Yes,
plot you
yes,
can put zero something, anything, whatever.
yes, clear. It's clear.
Yes. So next problem. So this is third part of this problems under same group action. So find intersection sigma belongs to S5, fixed point of sigma, which means the matrix is fixed under the action of all the permutation of S5. Matrices which are fixed under all the action of S5. So can you do this? I guess this should be obvious for you now. Tell me.
Yeah, is this the stabilizer
Stabilizer of what?
of S5
Stabilizer, we compute the element of set, but this is asking the fixed point of what?
of the
Sigma
sigma?
permutation. Yes. So these are fixed point are basically element of the set, and stabilizer is a subgroup of a group. Both are different things. So can you see? Same action, same thing, everything is going to be same. So you have to compute matrices which are
So
fixed under the
it
action.
will be basically all the columns are same.
So all the columns have same. Right, that's correct. How you concluded this?
Because we are taking any of the actions, so we don't know from beforehand which columns
All columns
we
are
can
going to
separate.
be
Yeah,
exchanged because
yeah.
there is permutation at least 1 2 3 4 5 is there, so
Yeah.
that will permute all the columns. So basically every column is getting to permute. So there is only how many matrices are there?
So
So how
that's
many
5 to the
matrices?
power 5.
Yes. So this is 5 to the power 5. Justification is all columns are exchanged under abstraction. So if the matrix has to be fixed under the group action, all columns have same entry, should have same entry. So total number of all such matrices equals to 5 to the power 5. So now, yeah, that's good. We have done this. So now this is an okay. Now do the problem. We do the problem of burnside lemma. Then we go to again the back the theory of what we are doing, discharging method and its application. So let's do this problem of burnside lemma. Then go to again back. Or if you don't want to discuss this group theory problem more, or we can discuss if you have any doubt on group theory problems also. So let's do this question. So consider a 4 cross 4 chessboard and let X denote the set of all possible non-attacking four rook placement on the board on the board any two non-attacking rook placement in X are said to be equivalent if one can obtain from other by 0 degree, other by 0 degree or 180 degree anti-clockwise rotation of the chessboard. Find the number of non-equivalent four rook placements. Number of non-equivalent four rook placement. Yeah, so this is the problem. So what is the problem asking you? Have you understood? Okay. So have you understood the problem? I guess he's not there.
Yes, I have understood.
Okay. So what is the problem asking? So we have given a 4x4 chessboard and X denote the set of possible non-attacking four rook placement on the board. So then any two non-attacking rook placement in X are said to be equivalent if one can obtain from other by 0 degree or 180 degree anti-clockwise rotation of the chessboard. Find the number of non-equivalent four rook placement, right?
Yes.
So what do you mean by non-attacking rook placement? Have you understood?
Yes, they are not in the same vertical or horizontal position.
Okay, good. Okay, so let's do the problem. Have you understood so this should be clear 180 degree or 0 degree rotation. So you try to use the burnside lemma. What we have to compute? Find the number of non-equivalent four rook placements, right?
Yes.
So under 0 degree, everything is getting to be fixed, but under 180 degrees, some two different things are can be get. So what is this burnside lemma? I have written somewhere, right? Where I written? I write somewhere burnside lemma. Where I have burnside lemma. This one. So this one. Try to use this y mod g cardinality is same as cardinality of this pi belongs to g fixed pi. Here our g is only two things, right? 0 degree rotation and 180 degree rotation. This thing forms a group. Can you see? A rotation of a square along 0 degree and 180 degree. This thing forms a group. Can you see?
Yes.
Because the composition is basically 0 degree identity and all things are there, right?
Yeah, yeah.
So this forms a group. So now here two elements you have in so fixed point, so fixed of 0 degree, and everything is getting will get fixed under 0 degree, right?
Yes.
Because this is identity only. And I 180 degree, how many are getting fixed that you have to identify, right?
Yes.
So then we can use this. That will give you number of uh, that will give you what? Number of
So
orbits under this action. So what is this action? This action is exactly the number non-equivalent for root placement, right?
yes, yes.
This orbits, basically number of orbits is number of non-equivalent, because two things are identified if they are in equivalent root placement, basically they have, right? So
Yes.
let me explain you. Let me draw a square and draw pictures, then maybe things will become clear to you. Suppose this is 4 cross 4. 1, 2, 3, 4. So right. So suppose let me draw one thing, other one here, other one here. These all are so this is a 4 cross 4 chessboard, and all these four are non-attacking rook's position, right?
Yes.
So this is one thing. Another one similarly you can draw. Let me erase this and draw, because I am not want to draw again and again same picture. So let me draw second one. So what are other possible positions? I can put one here. Now if I do 180-degree rotation of this thing, suppose, okay, how this will look like if I draw 180-degree rotation of this thing?
It will stay the same.
Not still the same, but it will be anti-diagonal.
Oh, yes.
It will
Yeah,
be,
yeah. Uh,
no, it will be same. Sorry,
it will
sorry, sorry.
same, no? Yeah.
It will be same. In 90-degree, this will be anti-diagonal. Then again, it will be same, right?
Uh,
Yeah. So yes, that's correct. Then okay, let's draw. So this is again getting to identified with itself. So let me draw some other. So if you are putting one here, another one I can put here, another one I can put here, another one I can put here. I guess, let's say. So this is getting fixed again, right? Because this one will go to this one, and this one will go to this one
yeah.
under 180-degree. Can you see?
Yes. So
That's good.
the pattern is that as a matrix, the ij
And
position
GI
goes
should be
to
same. Yeah, that's
uh,
correct.
yeah. So ij goes to for I goes to 5 minus I, and j goes to 5 minus j. Basically, the function
Yes.
will
What you are
nothing.
saying? What you are saying?
So we have that for any position ij, the 180-degree rotation moves it to 5 minus I, comma 5 minus j.
5 minus I comma 5 minus C. Yeah, that seems correct to me as well. Yes. Uh, that's correct. That's correct. That's correct. Because this thing will do this. Okay. Yeah, this is correct. This is correct. So, but we have to find out what. So,
The number of um, placements, non-attacking placements.
yeah. So how you will do that?
Hmm.
Hmm. So for one side, okay. So for one side lemma, what we need to do? We need to find out fixed point of this. Okay, rho naught is basically 0 degree rotation, and fixed point of 180-degree, rho 180-degree. So we have to find out these two things for at least for one side lemma. Then we will do this. Okay, what is fixed point of rho 0? What is the cardinality of this thing?
Is it asking how? Uh, can you actually reiterate what the fixed point was counting? Was it counting the unique numbers of
It is counting rooks which are fixed under this 0 degree rotation.
all?
All rook placements, yes.
Yeah.
So this is what? How many rooks?
So, but because we are assuming that these are all non-attacking, right?
Yes, they are non-attacking.
So this is the answer that we are looking for.
No, we are not looking for this. We are looking for non-equivalent for rook placement.
Okay, so yes, yes. Yeah, so we are looking for a fix P naught minus fix P 180.
No, 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 not correct. Okay,
Uh, 180 counts the rook placements which are equivalent under the 180
180
degree.
degree rotation.
Yeah.
Rotation,
So
yes, yes.
P naught makes everything stay the same. So 180 counts the over counts, the ones that do indeed stay the same after 180 degree rotation.
What you are saying? Can you say again?
I was saying, I think we are looking for fix P, fix row 0 and row 1 minus fix row 180.
Okay, so what is that? Let's say. So what is fixed row 0 minus fixed row 180? What
This
is
is
this?
all the rook positions, basically, the left side.
This says that basically fixed row 180 basically rooks
All
which
the
are
non-attacking
fixed
rook
under
positions.
180 and fixed row 0 is which are fixed basically all permutations.
Yeah,
So all minus you are removing the rook placement which are fixed under 180. So this
yeah.
remains the rook. So these are basically rooks which are not fixed under 180. So these are rook placements which are not fixed under 180. But we are not asking this now. We didn't ask this, right? Have you asked this?
If then okay, so I guess in when I first said that we are looking for fix row 0, I suppose then that
Hmm?
was correct, right?
No, this is not correct.
Because
Fixed row
if you
0 in fixed row 0 two rook placement which are equivalent, they can be different in row 0, right? Like these two, like how I should say, in row 0 computes all rook placement basically, right?
yes, we are looking for all valid rook placements.
We are looking non-equivalent rook placements. They can be equivalent as well under 180-degree rotation.
Equivalency is defined if after rotation they stay the
They
same.
remain same. Yes. So this is computing all thing as a different. This is computing this thing and this thing, another thing as a different thing. 0 degree one. After 180 degree, they are getting same.
Okay.
So fixed row 0 is basically what? First one, in first row we have 4 choices, we can place anywhere. But in second row we have only then 3 choices because we cannot put it just below this one. So we have 3 choices. In third row we have 2 choices. In fourth one we have only 1 choices. So this is precisely 4 factorial, right?
Yeah.
And fixed row in 180, how much choices we have?
Uh,
That we need to compute. How will compute this? Uh,
there was one lesson where we computed the reflections along the diagonal of the matrix or something
yes,
similar.
we computed something like that. Yes, 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 yes.
There was what paths or works, I actually forgot. Mm,
So, this grid path basically we
yeah,
have
grid
computed.
paths. Yeah.
Yeah, but how to do that? I forgot these things. Uh-huh. What are these? How many grid paths we have there? So what is the formula for that? I forgot.
Yeah, the grid paths that don't cross the diagonal.
Yes. Uh, I didn't recall what is the formula for that. But can we see without that this spell which are fixed under 180? So let's see what are the possible positions which are fixed under 180. So what positions we should put if you want to fix 180, right? If you see that we are done, right? So for in first row, if I put here in first row, I put any four slot. Let's say first one, any four slot are choices. Then in second one, where I have to choose, I have some restriction then, right?
First one
Because
and last one are fixed.
okay, so once I fix first one, then I have to fix fourth one also, right? Because
Yeah.
that is automatically
Okay.
getting
So
fixed.
also we can notice that wherever we fix the second one, the third one also gets fixed by symmetry. So we only need to count the second one, right?
We have first one and second one choices, right? I guess. Yes, that seems correct. But for second one, not all choices, right? Because we cannot put below just that. And first
Along
one
the
we have
diagram.
first one we have four choices. That is clear. Na? Hello.
First one we pick four choices. Are if you
Yeah. In
restrict by first, but if you mean by first one that all the other so your rooks have to be to the right of it, then I don't see that. But if you mean
but I haven't said now all the routes to be right to this. The problem
no,
doesn't said.
if you want to place all the four rooks,
Huh? First one I can place anywhere. Like this kind of arrangement can I also did, right? All thing, one thing here, one thing here, one thing here, one thing here, something like that. This is also fixed under 180, I guess. Yes, this is fixed under 180. Yeah, yeah. This is correct.
first one is limited in the first column, I think.
No, not correct. Right?
If you empty the first column, then you cannot have the
Have
configuration, right?
what? Cannot have what?
Cannot have a valid configuration if you remove the first, if you keep the first column empty.
I'm not keeping first column empty. Some entry will come at first column that I'm not, because that will come naturally, right? That will come basically. If you are putting anywhere first first, then the second one should cannot come below this. At last fourth one, somewhere it should come below that. Basically, that's what I'm saying. Because all rent entries cannot be in same column. So first column cannot be empty basically, because we have only four column, four rooks. One column cannot have two rooks. So every column should have one rook at least.
Okay.
So I'm not saying first column is empty. I'm saying first row have all four choices. Rook can be placed anywhere.
So suppose you place the rook at first column, second
Hmm.
position, second row or third row, then it isn't in 180-degree, right? It can only be along, yeah, the
Okay,
first.
let's do what you are saying. You are saying place me first rook on first row, second column, right? That's what you said.
Yes.
So, so what you want now?
Then
I am saying under
it will
rotate
force that the
under
so
one under 180 degree. This will say that fourth row is getting here, right?
yeah, fourth. No, I'm saying if you want to keep this under same under
Six.
180 degree
So
fixed,
that
yes.
means yeah, this should come under fourth row. Rook should be placed here. That's what
Yeah,
I'm
yeah,
saying.
yeah. That will move to here.
So I am saying that first row have four choices. That will automatically fix the fourth row basically.
Yes.
That's correct. Are you
Yeah.
getting this or not?
Yes. Yes.
Now things remain for second and third row, right?
Yeah.
So so once I am fixing first row, then second row have only three choices because cannot come below just below this, right?
Yes.
But I am saying it should have only two choices. How to argue for this? I feel that this should have only two. Are you also thinking that? But I feel because uh, how to say? How to say? How many choices this second row have? If I put somewhere here, then how, where I should place another one? That should place here, right?
Yeah.
If I, okay, uh, okay. If I put somewhere here, then where I should place third one? I cannot place this one. Ah, this, yeah, two choices are already get. So the second one have two choices. This is obvious, right?
You
Why you are
cannot.
not saying to me? Yes, these two columns are already get cancelled. So this one and this one are only possible choices, first and fourth one, right?
Yes.
So only two choices this have, and every choice is valid choice basically. Because if you place here, then another one will come here. If you place here, then another will come here in 180 degree. Because we need to fix it in 180 degree, right?
Yeah. Yeah. Only two choices. Yes. Correct.
So have you got this?
Yes.
So we have computed this fix 180 degree. This is 4 into 2. So yes. So now what we are saying, what we need to compute, we need to find out number of non-equivalent four root placement. Number of non-equivalent four root placement. Two root placements are equivalent if they lies in same orbit under the action of the group, action of group rho 0 and rho 180 on chessboard. So this is equivalent. So number of non-equivalent four root placement is same as number of different orbit is same as number of different orbit in this section, number of distinct orbit in this action which by burnside lemma is equals to 1 by 2 cardinality of the group which is 2 rho 0 plus rho 180 which is equals to 1 by 2 4 factorial plus 8, so which is 4 तियम 12 दूना 24 8 32 बट्टा 2 16. So yeah, this is the answer. So is this clear or any doubt you can ask?
Yes. It's clear.
Clear na?
So, can you explain the orbit again?
Yes. So two things are equivalent if they are like two root placements are equivalent if they are same under rho 180 basically, right? 180 degree rotation.
Yeah.
So that means they lie in same orbit.
I'm just asking the idea of orbit.
Okay, what is orbit? Okay, so you know definition na or not?
You explained, I think earlier, but I'm not
Yes,
sure.
orbit of an element x. Suppose x is here one root placement.
Okay.
In your mind, fix one root placement. So what
Yeah.
is the orbit of this root placement is basically is g dot x. G dot x is an element of x. Basically, this is another root placement such that g belongs to g. So you here g is here, g is your rho 0 and rho 180. So what? So orbit of x can be at most two cardinality set. because row 0 is fixing that hook placement, and row 180 is 180 degree rotation of that hook placement, right?
Yeah. Oh, suppose
So
then I suppose for a rook placement, the cardinality of orbit can be 1 or 2. 1 if the rotation
also fixes
does
that,
not
right?
change the
Yes, yes, yes,
placement. Yeah, yeah.
yes,
Okay, okay.
yes. So that's correct. In fact, you can prove the in any group the cardinality of the orbit is a divisor of group. Should have a
What?
divisor of group.
Okay. Divisor
Try to
of a
prove
group
all.
means as
Should
a
be divisor.
operator.
Should be the cardinality of the orbit should be divisor should be divisor of the size of group. matlab, how to say this? This should be correct, na? So suppose cardinality of orbit is d, then in size of group is n. So then d should divide n basically.
Okay.
That's what I
Yeah,
meant.
yeah.
Huh. So this is what. So now we want to find number of non-equivalent root placement. So that is same as
The
number
number
of,
of orbits. Yes. Yeah.
yeah. So now it is clear.
Yeah.
Good. So this is an application of burnside lemma. So now let's go to these back to these problems in your course, which are about planar graphs and all that. Huh. So question: prove that triangle free planar graphs are four colorable. Prove that triangle free planar graphs are four colorable. So this is the problem. Yes. So hint is given in this problem that there prove that there exists a vertex of degree at most 3 using discharging method, he is saying. Prove that. So first let's prove this claim what he is suggesting. He is saying this thing, hint as this thing. There exists a vertex of degree at most 3. There exists a vertex in a graph. Let's name this as a G. There exists a vertex of degree at most 3 in G. So can you prove this? Can you hear me?
Can you say again?
So can you prove this claim at least? There
Uh,
exists a vertex of degree at most 3 in G, where G is a triangle free planar graph.
mm, there is this is uh this is similar.
Last time I have proved that any planar graph have a vertex of degree at most 5. Now this is somewhat more getting restricted. This is saying that triangle free, then this have a vertex of degree 3. You can prove by charging discharging method or something Euler characteristic, also Euler identity. You can try by Euler identity. That should be easy, I guess. You recall Euler's identity, right? What is that? E minus E plus F is 2. Number of vertices minus number of edges plus number of hashes is 2.
Yes.
So can you do now? Go for contradiction. Suppose if every vertex have degree greater than 3, that means every vertex have degree greater
At
than
least
equals
4.
4. Yeah.
Yeah.
So that means this small delta G is greater than 4, right? So what will happen? So just use this one also. So V minus E plus F is 2. So multiply this one is by minus 4. So what will this happen? So this will be minus 4V plus 2E plus 2E. I am writing this in this way, plus minus 4F is equals to minus 8. So now what is V? Okay.
So
So what is the relation? 2 times degree V is E, right? Sorry,
2
degree
times
V
E
is
is sum of all vertices, degree of vertices, right?
right. So this is the relation, minus 4V plus summation V belongs to V dV,
Yeah.
and the
Times
huh,
times 2.
so 2E minus 4F. But I am going to write here something. Try to observe this if it is clear or not. Otherwise, I to prove dV. This is clear, but this thing is greater than summation over faces. F belongs to F, length of faces. Is this clear or not?
Yes.
This should be clear, right?
Yeah. The that side is twice the edges, and that side is basically the length of edges. Okay. Yeah. Yeah.
Length of face is number of edges.
Yeah.
Yeah. So is this clear?
Yes.
So this is summation F belongs to F, length of faces minus 4F is equals to minus 8. This is what we have, right?
Yes.
So now what is this? What is this? Can you write in? So this is summation V belongs to V dV minus 4 plus summation F belongs to F LF minus 4, right?
Yeah.
Is equals to minus 8. Now what? We have given that every vertex had degree greater than 4, right?
Yeah.
Because we assume that the
This
condition
is,
doesn't
yeah,
hold.
the right hand side can be negative.
Yeah. So this LHS cannot be negative.
Yeah.
LHS is non-negative, which is contradiction. Which is contradiction. So that means what? There should exist a vertex of degree. That means
3.
yeah, there exists a vertex of degree
At most 3.
at most 3. But now what we need to prove? We need to prove that G is triangle free planar graph, then it has 4 coloring. So how to prove this now? Last time we have proved for 5 coloring. So how we prove that? We get some restriction on degree, then we apply induction. Here we also got restriction on degree. Now we have to go for induction, right?
Yes.
Can you see the proof now? How to, on which we have to apply induction? Can you see on this thing I have to apply induction? Base case is obvious, na?
Yeah, now the number of base case in the number of degrees is obvious, I suppose. Yeah.
What, apply the induction on number of vertices.
Yeah, number of vertices. Yes, I meant to say vertices.
Yes. Base case is obvious. Suppose true for n, then go for n plus 1. But from n plus 1, remove this degree 3 vertices, because there should have some degree 3 vertices. Then remaining one have 3 coloring by this. Remaining one have what? Remaining one is 3 colorable. Remaining one is how much colorable? 4 colorable, right? By this induction hypothesis. So once you join the since this vertex have degree 3, so this is going to be connected at at most 3 neighbors. So this is going to connected exactly 3 neighbors since degree is 3. So it have remaining fourth color remaining. So this fourth color can be chosen from these things which are not in these 3 adjacent neighbors, right?
So after the suppose the n vertex case is the hypothesis. When we
Huh?
add n plus one case, when we add another vertex, what do
Huh?
we suppose that
So, so,
vertex?
so, so, so this vertex have a this graph has a vertex of degree 3 by this claim, right? Which we have proved.
Yes, but the thing is, in the n plus one graph, which there is there, if we assume it to be constructed from the previous graph.
No, we are not assuming constructed from previous one.
Okay, okay, okay.
We are taking any n plus one graph.
Any n, yeah, yeah.
But when we are restricting to this n cardinality graph, n vertices graph, then this should have this induction hypothesis holds, na?
Yes.
But apply and remove the vertices corresponding to degree 3, then remaining one have 4 coloring. But since this vertex have degree 3, so this can have only 3 neighbors. So that means this fourth color is remaining, which you can color it, and this is 4 coloring, right?
Yeah, yeah.
So is it clear?
Yes.
So apply induction on number of vertices. So base case done. Assume true for n, then for a graph G with n plus 1 vertices, uh, remove the vertex corresponding to degree 3, to degree 3, then remaining one is 4 colorable by hypothesis. Remove the vertex corresponding, but the remaining one is 4 colorable by hypothesis. But since degree p is equals to 3, that means so p has only 3 neighbors. So color it with one remaining color in color, that is, so this implies G is 4 colorable. So yeah, we are done. So let me give you this, leave with this example, and hope you will try it. You can try to do it as exercise. If not, you can ask me next time. So I defined you this group S5 now. So on this S5 group, you can consider this action. So sigma 1 acting on, let's say, some permutation tau, sigma acting on, I should say, G acting on G itself by sigma comma tau goes to sigma tau sigma inverse. So what are the tasks for you? So find orbits, stabilizers for this action.
What is the can you repeat what was the tau?
Tau is any permutation, sigma is also permutation. Sigma belongs to G, tau belongs to G, because same group acting on itself. Na?
Okay,
First
okay.
one I defined by just by left multiplication. Now I am giving you another action. First you can try to first you prove that this is a group action of G on itself. Then this action is find orbits under this action. These are called conjugacy classes.
Uh,
The orbits under this action are called conjugacy classes. This is a special action called conjugation action, and orbits under this action are conjugacy classes, and stabilizer of this action try to find out that. But these actions are basically important, right? So conjugation action. Suppose you are in GLNQ, GLNQ, let's say. So you know, if two matrices are equivalent in GL and Q, basically they lie in same conjugacy class. Try to prove this. All these things are well known fact in group theory. This you can even prove easily. GL and Q, two matrices are equivalent. They are lies. That means they lies in the same conjugacy class if and only they have same determinant. But now change your ring to GL and Z. This problem become harder. And in fact, I feel recently, at least 4 5 days ago, one of the postdoctoral fellow discussing this problem with me, and this seems open problem to us because this goes to something like ideal class group in number theory. We tried to discuss it, and then it went to somewhere there. And so he is interested in some hyperbolic geometry stuff. So these groups are interested for them: GL and Z, GL and Q, SL and Z, something like that. But the thing is that you are not in field. Z is not field. Z is just a ring. So these things are become complicated. Finding conjugacy classes become harder. Even I defined you Sn. This has a subgroup An, which are basically even permutation. For finding conjugacy classes for them is also slightly tricky, more harder than S5, Sn. For Sn, you can prove some results which are more, which give you best help to compute conjugacy classes. So what is the number of conjugacy classes in Sn is equals to partition of the natural number n. You understand the meaning of partition?
Yeah.
Oh, okay. So try to prove this result also. Number of conjugacy classes in Sn is equals to partition of the natural number n. Now, suppose you have given one permutation sigma in one, let's say 1, 2, 3, 4, 5. So what I mean by its cycle type, so this, I am saying that this is a cycle type of 3, 1, 1. That means it have a cycle of length 3 and two cycles of length 1, 1. Right? This is
Yes.
the meaning of cycle type. So another theorem which you can try to prove, and these are easy proofs. That's why I am giving you. That will give you motivation to read group theory. So two permutation. So so two permutation in Sn lie in same conjugacy class if and only if they have same cycle type. If you prove this theorem, then this previous one is obvious. Then this one is obvious. This will imply this. Right?
Okay.
This proof you can see. This implies this one you can see, right? Two permutation in SLI in same conjugacy class if and only they have same
Yeah,
cycle
yeah,
type.
yes.
This one will imply this one.
Yeah. This
Yes.
is the
These
cycle
are,
type corresponds to a partition, basically.
yes,
Yeah.
yes. In SN, then you can try for AN. Okay, let me describe the group AN for you, and then you can also try for AN. So AN is a subgroup of SN. Subgroup you know na.
Yes.
And now another fact here which is easy to prove. Any permutation in SN can be written as a product of two cycles. Two cycles means two length cycles. Suppose you have given this 1, 2, 3. Let me 1, 2, 3 in S3. So I am asking you to write it as a product of two cycles, basically two length cycles. So how you will write? Can you write?
Product of two length cycles.
Yes.
So one, so
Basically
one,
composition of two functions.
yeah.
Two length cycles means one element should get fixed. So can you write?
One element should get fixed.
That's what means two length cycle. Na? Two cycles means two length cycles basically. I should say two length cycles. Two cycles means
Yeah,
two
yeah,
length
yes,
cycles.
yes, yes.
Huh. So can you write some with
So, suppose
one
one
pro
one example
how to
would be
write
one and then two, two, three,
what you are saying? One,
and then two, three.
but this is different one. You have to write as a product of 2, 1. So how you will write? This is a different one. 2, 3 and 1, 3 you want to say. So what is this? If you write 2, 3 and 1, 3. So what is this? 1 goes to 3, 3 goes to 2. So this is 1 goes to 3, 3 goes to 2. So this is 1 goes to 2, 2 goes to 2 and 2 goes to 3. So 2 goes to 3 and 3 goes to 1, 1 goes to 1. So that's correct. So this is a
Okay.
correct
Oh,
product.
okay.
So in general, I am giving you hint. You try to prove this. In general, any permutation of the form 1, 2, so on n. This can be written as 1n, 2n, so on in this form. Corresponding product. Prove this thing. This all things you can do. Something like this. This is easy observation. So any permutation can be written as a product of 2 cycles. So what are an? An are collection of all even permutations. Even permutation means permutation
Even
which have a even number of cycles, even number of 2 cycles. Even permutation means
even number of cycles.
2 cycles. Like this
Yeah.
permutation is a
Yeah.
even
Yes.
permutation
Yeah.
because this have two cycles, but its length is odd. But that means it has. So that means basically odd length cycles are even cycles. Odd length cycles are even permutations, right? Which can be written as a cycles which have odd length, permutation which have odd length are even permutations, right? Because
Yes.
they can be written as a product of
Yeah.
even many 2 cycles. Even permutations are permutations which can be written as permutation which can be written as a product of even number of 2 cycles. So now, so then prove that this an is a subgroup of Sn and try to find out under same action, basically action of an on an above, which I define above by conjugation sigma x on tau, basically by sigma tau sigma inverse. Under this action, find its conjugacy class. These all are interesting problems. So I hope with this I will stop here. Thank you. Let me stop recording
Yes.
and stop recording. Yes. Yes.